Greetings, curious humans. Today, we are diving into the fascinating world of the Kepler Telescope. Named after the renowned astronomer Johannes Kepler, this extraordinary space observatory was launched by NASA in 2009. Its mission? To hunt for exoplanets, those distant worlds orbiting stars beyond our own. Let's embark on a cosmic adventure and uncover the groundbreaking achievements of the Kepler Telescope. During its 9-year mission, Kepler revolutionized our understanding of the universe. By monitoring the brightness of over 150,000 stars simultaneously, Kepler detected thousands of exoplanets, ranging from rocky worlds to gas giants. It provided valuable insights into the prevalence of exoplanets, their sizes, compositions, and potential for habitability. Join us as we explore the challenges Kepler faced and the ingenious solutions devised by NASA. From the issues with its reaction wheels to the remarkable K2 mission, Kepler continued to expand our knowledge and reshape our view of the galaxy. Get ready to delve into the captivating story of the Kepler Telescope, its groundbreaking discoveries, and the profound impact it has had on our understanding of the universe. This is going to be an adventure of astronomical proportions. Make sure to subscribe to our channel and hit the notification bell to stay updated with our cosmic explorations. Let's begin our journey into the incredible world of the Kepler Telescope. The Kepler Space Telescope was launched by NASA in 2009 with the goal of discovering Earth-sized planets orbiting other stars. It operated for 9.5 years until its fuel was depleted, and NASA announced its retirement on October 30, 2018. Kepler's main objective was to survey a portion of the Milky Way galaxy to identify Earth-sized exoplanets in or near habitable zones. It used a photometer to monitor the brightness of around 150,000 stars, looking for periodic dimming caused by exoplanets passing in front of their host stars. During its mission, Kepler observed 530,506 stars and confirmed 2,778 exoplanets as of June 16, 2023. The construction and initial operation of the telescope were managed by NASA's Jet Propulsion Laboratory, with Ball Aerospace responsible for developing the Kepler flight system. The Ames Research Center handled ground system development, mission operations, and scientific data analysis. The telescope faced several challenges during its mission. In 2012, one of the spacecraft's reaction wheels stopped turning, and in 2013, a second reaction wheel failed, disabling the collection of scientific data. NASA decided to modify the mission and requested alternative proposals from the space science community. The K2 second light proposal was eventually approved, allowing Kepler to continue searching for exoplanets using the remaining functional reaction wheels and thrusters. By January 2015, Kepler had confirmed 1,013 exoplanets in about 440 star systems, with an additional 3,199 planet candidates. The mission provided valuable data on exoplanets and contributed to our understanding of supernovae. On January 6, 2015, NASA announced the discovery of the 1,000th confirmed exoplanet by Kepler, including 4 planets within habitable zones. On October 30, 2018, Kepler was retired after running out of fuel. Despite the retirement of Kepler, NASA launched a new mission called TESS, Transiting Exoplanet Survey Satellite, in 2018 to continue the search for exoplanets. The Kepler Space Telescope has a mass of 1,039 kilograms, 2,291 pounds, and features a Schmidt camera with a 0.95 meter, 37.4 in, front corrector plate feeding a 1.4 meter, 55 in, primary mirror. At the time of its launch, this was the largest mirror on any telescope outside Earth's orbit. The telescope has a field of view of 115 deg2, equivalent to the size of one's fist held at arm's length, with 105 deg2 of science quality and less than 11% vignetting. Kepler's photometer is designed for excellent photometry rather than sharp images, with a soft focus. The focal plane of the spacecraft's camera consists of 4250 by 25 mm, 2 by 1 in CCDs with a total resolution of 94.6 megapixels, making it the largest camera system launched into space at the time. The CCDs are cooled by heat pipes connected to an external radiator. The primary mirror of Kepler is 1.4 meters, 4.6 feet, in diameter and is made of ultra-low expansion, ULE, glass manufactured by Corning. It has a very high reflectance coating consisting of a protective 9-layer silver coating and a dielectric interference coating to enhance reflection and minimize color centers and atmospheric moisture absorption. In terms of photometric performance, Kepler performed well but fell short of its design goals. The objective was a combined differential photometric precision, CDPP, of 20 parts per million, ppm, on a magnitude 12 star for a 6.5-hour integration. However, the actual accuracy varied depending on the star and position on the focal plane, with a median of 29 ppm. The noise level was higher than expected, primarily due to larger than anticipated variability in the stars themselves. The Kepler mission required a longer duration than initially planned to detect all transiting Earth-sized planets. The spacecraft orbits the Sun in an Earth-trailing orbit, slowly falling behind Earth. It avoids Earth occultations, stray light, and gravitational perturbations and torques associated with an Earth orbit. Kepler's field of view was initially directed towards the constellations of Cygnus, Lyra, and Draco, away from the ecliptic plane, to avoid sunlight entering the photometer as the spacecraft orbits. The telescope's orientation is 3-axis stabilized using fine guidance sensors on the instrument focal plane and reaction wheels and hydrazine thrusters to control its orientation. The Kepler Space Telescope was operated by the Laboratory for Atmospheric and Space Physics, LASP, in Boulder, Colorado, under contract to Ball Aerospace and Technologies. LASP and Ball Aerospace controlled the spacecraft from a Mission Operations Center at the University of Colorado. The mission's initial life cycle cost was estimated at $600 million, including funding for 3.5 years of operation. Communications with the spacecraft were carried out using X-band and Ka-band links. NASA contacted the spacecraft twice a week for command and status updates, while scientific data were downloaded once a month at a maximum data transfer rate of approximately 550 kb/s. The high-gain antenna was not steerable, so data collection was interrupted for a day to reorient the spacecraft and the high-gain antenna for communication with Earth. The science data collected by the spacecraft were sent to the Kepler Data Management Center, DMC, at the Space Telescope Science Institute in Baltimore, Maryland. The DMC decoded and processed the telemetry into uncalibrated FITS format science data products, which were then passed to the Science Operations Center, SOC, at NASA Ames Research Center for calibration and final processing. The SOC performed analysis algorithms to produce calibrated pixels and light curves for each star, conducted transit searches for planet detection, and evaluated data validation of candidate planets. The SOC also monitored the photometric performance, developed and maintained the project's scientific databases, and returned calibrated data products and scientific results to the DMC for archiving and distribution to astronomers worldwide through the Multi-Mission Archive at STSCI, MAST. Kepler faced challenges with reaction wheel failures. On July 14, 2012, one of the 4 reaction wheels failed, and on May 11, 2013, a second wheel failed, ending Kepler's primary mission. Efforts were made to recover the failed wheels, but they were deemed unrecoverable. This led to the follow-on mission called K2, which observed different fields near the ecliptic. After delays in the project's launch due to budget cuts and fiscal issues, Kepler was successfully launched on March 7, 2009. The observatory's cover was jettisoned on April 7, 2009, and the first light images were taken the following day. The focus of the telescope was optimized by adjusting the primary mirror's position and tilt. Kepler completed its commissioning phase on May 13, 2009, and began its search for exoplanets. During its mission, Kepler downlinked approximately 12 gigabytes of data about once per month. The Kepler Space Telescope had a fixed field of view, FOV, covering 115 square degrees, which is approximately 0.25% of the sky. Its FOV included portions of the constellations Cygnus, Lyra, and Draco. The mission website provided a calculator to determine if a given object falls within the FOV. The primary objective of the Kepler mission was to explore the structure and diversity of planetary systems. It aimed to determine the prevalence of Earth-size and larger planets in or near the habitable zone of different types of stars, study the range of sizes and orbits of these planets, estimate the occurrence of planets in multiple star systems, investigate short-period giant planets, identify additional members of discovered planetary systems using other methods, and understand the properties of stars hosting planetary systems. Kepler focused on detecting smaller planets, ranging from 30 to 600 times less massive than Jupiter, closer to the size of Earth. It used the transit method, observing the repeated dimming of stars as planets passed in front of them. By analyzing the reduction in brightness in the interval between transits, Kepler deduced the size, orbital period, semi-major axis, and temperature of the planets. Kepler's field of view significantly increased the probability of detecting Earth-sized planets compared to other telescopes like the Hubble Space Telescope. Kepler observed approximately 150,000 stars out of the 500,000 stars in its field of view, with a preference for G-type stars on or near the main sequence. The spacecraft measured variations in their brightness every 30 minutes to capture transit events. While the initial reported results focused on larger Jupiter-sized planets in close orbits, Kepler expected to discover smaller planets and those farther from their Sun over an extended period. The mission also utilized its data to study variable stars of various types and perform astroseismology, particularly on stars showing solar-like oscillations. After collecting data, Kepler processes the raw light curves by adjusting brightness values to account for spacecraft rotation. The light curves are then folded into a more manageable form, and potential transit-like signals are identified as threshold crossing events. These signals undergo 2 rounds of inspection to eliminate non-signals, instrumental noise, and eclipsing binaries. Signals that pass these tests are designated as Kepler Objects of Interest, KOIs, and archived. KOIs then undergo a more thorough inspection process called dispositioning. Candidates that pass dispositioning are labeled as Kepler planet candidates, although the KOI archive is dynamic, and candidates can be reclassified as false positives and vice versa. Not all planet candidates go through this process. Circumlunar planets, which do not show strictly periodic transits, require alternative inspection methods. Researchers may also use different data processing techniques or search for planet candidates in the unprocessed light curve data, potentially resulting in missing KOI designations. To confirm planet candidates and rule out false positives, follow-up tests are conducted. Ground-based telescopes are often used to image individual Kepler candidates and resolve any background objects that could affect the transit signal. Astrometry, the study of stellar motion, can be employed to determine if a transit is caused by a stellar mass object. Other detection methods, such as Doppler spectroscopy and transit timing variation, can provide additional evidence to confirm planet candidates. Doppler spectroscopy requires follow-up observations and works well for massive planets or those around relatively bright stars. Transit timing variation examines the time between successive transits and can confirm low-mass planets, especially in multiplanetary systems. Circumlunar planets exhibit significant variations in transit timing and duration due to the orbital motion of their host stars. These patterns help confirm their presence. Reflected light variations, similar to lunar phases, can be observed for planets close to their stars. This method may contribute to discovering more planets in the long run. Kepler's photometric precision allows for the observation of brightness changes caused by Doppler beaming or star deformation by a companion, helping to rule out certain false positives. If a planet cannot be confirmed through other methods, validation is done by assessing the likelihood of a Kepler candidate being a real planet compared to false positive scenarios. Confirmation can also be achieved by observing the transit with additional telescopes or through the validation by multiplicity method, which relies on the observation that planets in most systems orbit in a flat plane. A new validation method called PASTIS has been developed, which can confirm a planet based on a single candidate transit event, although it requires a high signal-to-noise ratio. This method has been successful in validating certain planets. Overall, the process involves multiple steps of data analysis, inspection, follow-up observations, and confirmation techniques to establish the authenticity of Kepler planet candidates. In 2009, the Kepler mission announced its initial discoveries, confirming the existence of the known exoplanet HAT P7b and demonstrating the capability to detect Earth-sized planets. Variable stars that could interfere with the detection of small changes in brightness were identified and removed from the target list. The light curves of the dropped stars were publicly released. The first new planet candidate observed by Kepler, initially marked as a false positive, was later confirmed as Kepler 1658b. In the first 6 weeks of data, Kepler identified 5 previously unknown planets, all located close to their stars. These discoveries included one of the least dense planets found, 2 low-mass white dwarfs initially thought to be a new class of stellar objects, and Kepler 16b, a well-characterized planet orbiting a binary star. In 2010, Kepler released data on nearly 156,000 planetary target stars, excluding around 400 for follow-up observations. Among the released targets, 706 had viable exoplanet candidates with sizes ranging from Earth-sized to larger than Jupiter. Some candidate multi-planet systems were identified, including additional exoplanet candidates. The results from the released data indicated that small candidate planets with periods shorter than 30 days are more common than large candidate planets with the same periods, contrary to previous theories. This suggested that small and Earth-sized planets are more abundant than previously believed. However, it should be noted that the data did not confirm the discovery of Earth-like planets at that time. Additionally, Kepler identified 2 systems, KOI-74 and KOI-81, which contained objects smaller and hotter than their parent stars. These objects were likely low-mass white dwarfs resulting from past episodes of mass transfer in their systems. Overall, these early results from Kepler provided valuable insights into the frequency and characteristics of exoplanets and challenged previous assumptions about their distribution. In February 2011, the Kepler team announced the analysis of data taken between May and September 2009, revealing 1,235 planetary candidates orbiting 997 host stars. Among these candidates, 68 were approximately Earth-size, 288 were super-Earth-size, 662 were Neptune-size, 165 were Jupiter-size, and 19 were up to twice the size of Jupiter. The majority of the planets were smaller than Neptune, challenging previous assumptions. Additionally, 54 candidates were identified in the habitable zone, expanding the potential number of Goldilocks planets that could support liquid water. By December 2011, the Kepler team had discovered 2,326 planetary candidates, including 207 similar in size to Earth, 680 super-Earth-size, 1,181 Neptune-size, 203 Jupiter-size, and 55 larger than Jupiter. The number of Earth-sized and super-Earth-sized planets increased significantly compared to earlier figures. The team also found 48 planet candidates in the habitable zones of surveyed stars. Kepler 20e and Kepler 20f, the first Earth-sized exoplanets, were discovered orbiting the Sun-like star Kepler 20. Based on Kepler's findings, estimates were made that within 1,000 light-years of Earth, there could be at least 30,000 habitable planets. The number of potentially habitable planets in the Milky Way was estimated to be at least 50 billion. It was also suggested that 1.4 to 2.7% of Sun-like stars could have Earth-sized planets in their habitable zones, amounting to 2 billion Earth analogs in the Milky Way alone. In 2012, the Kepler team reported a total of 2,321 candidates, with 207 similar in size to Earth, 680 super-Earth size, 1,181 Neptune size, 203 Jupiter size, and 55 larger than Jupiter. The team estimated that 5.4% of all stars host Earth-sized planet candidates, and 17% of stars have multiple planets. A study suggested that the Milky Way may contain as many planets as it does stars, resulting in 100 to 400 billion exoplanets. Kepler 69c, an Earth-sized exoplanet orbiting a Sun-like star in the habitable zone, was announced as a candidate. In April 2013, 3 Earth-sized exoplanets, Kepler 62e, Kepler 62f, and Kepler 69c, were discovered in the habitable zones of their respective host stars, making them potential candidates for liquid water and habitable environments. On May 15, 2013, NASA announced that the Kepler Space Telescope had suffered a failure of a reaction wheel, affecting its ability to collect further science data. However, a backlog of data still existed, and more discoveries were expected to be made in the following years. In summary, during this period, Kepler made significant discoveries, including numerous exoplanet candidates and confirmed planets, including Earth-size and potentially habitable ones. It expanded our understanding of the prevalence and diversity of exoplanets and their potential for supporting life-sustaining conditions. In February 2014, over 530 additional planet candidates were announced, including nearly Earth-sized planets in the habitable zone. In June 2014, around 400 more planet candidates were added. On February 26, 2014, Kepler confirmed the existence of 715 new exoplanets using a statistical method called verification by multiplicity. This method relied on the presence of multiple planets in multiplanetary systems for faster confirmation. Among the discoveries, 95% of the exoplanets were smaller than Neptune, and 4 were less than 2.5 times the size of Earth and located in habitable zones. In March 2014, a study found that small planets with orbital periods of less than 1 day are usually accompanied by at least one additional planet with an orbital period of 1 to 50 days. On April 17, 2014, Kepler announced the discovery of Kepler 186f, the first nearly Earth-sized planet in the habitable zone, orbiting a red dwarf star. In May 2014, details about K2 observations fields 0 to 13 were released, and K2 observations began in June 2014. In July 2014, the first discoveries from K2 field data were reported, focusing on eclipsing binaries. By January 2015, the number of confirmed Kepler planets exceeded 1,000. 2 of the discovered planets, Kepler 438b and Kepler 442b, were rocky and located in the habitable zone. Additionally, in January 2015, 5 sub-Earth-sized rocky exoplanets were found orbiting the 11.2 billion-year-old star Kepler 444, making it the oldest known star system with planets. In April 2015, Campaign 4 of the Kepler mission took place, observing approximately 16,000 target stars and 2 open star clusters. In May 2015, Kepler observed the supernova KSN 2011b before, during, and after the explosion. On July 24, 2015, Kepler 452b, a confirmed exoplanet similar in size to Earth and orbiting in the habitable zone of a Sun-like star, was announced. The 7th Kepler Planet Candidate Catalog was also released, containing 4,696 candidates. In September 2015, astronomers reported unusual light fluctuations from the star KIC 846-2852, leading to speculation about the presence of comets, asteroids, or even an alien civilization. By May 2016, the Kepler mission had verified 1,284 new planets, including around 550 potentially rocky planets. 9 of these planets were located in their stars' habitable zones. The Kepler spacecraft, launched in 2009, had great success in finding exoplanets. However, in 2013, 2 of its 4 reaction wheels failed, crippling its extended mission. Without 3 functioning wheels, the telescope couldn't be accurately pointed. On October 30, 2018, NASA announced that the spacecraft had run out of fuel, officially ending its mission. In April 2012, a panel of senior NASA scientists recommended continuing the Kepler mission through 2016 to achieve its scientific goals. In November 2012, NASA announced the completion of Kepler's primary mission and the beginning of its extended mission, which lasted until 2018. The failure of two reaction wheels in 2012 and 2013 posed a significant challenge to the mission. Without three functioning reaction wheels, Kepler couldn't effectively search for planets. Various attempts were made to resolve the issue, including testing and evaluation of the remaining reaction wheels and thrusters. However, these efforts were unsuccessful, and in August 2013, NASA announced that Kepler would no longer search for planets using the transit method. Alternative ideas were proposed to utilize Kepler's remaining capabilities, such as searching for asteroids and comets, studying supernovas, and using gravitational microlensing to find large exoplanets. Modifying the software to compensate for the disabled reaction wheels was also considered. The previously collected data continued to be analyzed. In November 2013, a new mission plan called K2 or Second Light was proposed. K2 utilized Kepler's remaining capabilities for the study of supernovas, star formation, solar system bodies, and more exoplanet discoveries. The K2 mission involved searching a larger area in the plane of Earth's orbit around the Sun. In May 2014, NASA approved the extension of the Kepler mission to the K2 mission. During the K2 mission, campaign fields 0 to 13 were reported, and Kepler's photometric precision was estimated to be around 50 ppm for a 6.5-hour integration. In December 2014, the K2 mission detected its first confirmed exoplanet. In April 2016, Kepler experienced an emergency and entered into a safe mode. The cause of the emergency was initially unknown, but the spacecraft was returned to normal science operations after analysis and upgrades. In June 2016, NASA announced a 3-year extension for the K2 mission beyond the expected fuel exhaustion in 2018. In August 2018, NASA revived the spacecraft and applied modifications to deal with thruster problems. Kepler continued collecting scientific data for its 19th observation campaign, indicating that its onboard fuel was not yet fully depleted. The original plan for the Kepler mission was to release data within 1 year of observations. However, this plan was changed after launch, and data releases were scheduled up to 3 years after collection. This decision received criticism, leading to the Kepler science team releasing the third quarter of their data 1 year and 9 months after collection. Subsequently, data through September 2010 was made public in January 2012. Follow-up studies by other astronomers confirmed the existence of Kepler candidates. Astronomers used radial velocity data to confirm the existence of KOI 428b, later named Kepler 40b, and KOI 423b, later named Kepler 39b. Citizen scientists have also played a significant role in the analysis of Kepler mission data. The Planet Hunters project, launched in December 2010, allowed volunteers to search for transit events in Kepler images and identify planets that computer algorithms might miss. Users of the project discovered numerous potential candidates, previously unrecognized by the Kepler mission team. In January 2012, a public appeal on the BBC program Stargazing Live led to the discovery of a new Neptune-sized exoplanet by 2 amateur astronomers. Other volunteers continued to analyze Kepler images, leading to the discovery of exoplanets such as PH1b and PH2b. In April 2017, the Zooniverse Project Exoplanet Explorers was launched as part of ABC Stargazing Live. This project used recently downlinked data from the K2 mission, and volunteers helped identify transit candidates and even discovered a star system called K2-138 with 4 super-Earths. The Kepler Input Catalog is a searchable database used for the Kepler mission and contains approximately 13.2 million targets. It is not used solely for finding Kepler targets, as only a portion of the listed stars can be observed by the spacecraft. Kepler has also made observations of small solar system bodies and has been assigned an observatory code for reporting its astrometric observations to the Minor Planet Center. The NEO Kepler mission was proposed to search for near-Earth objects and potentially hazardous asteroids, utilizing Kepler's unique orbit and larger field of view. On October 30, 2018, NASA announced the official retirement of the Kepler Space Telescope, as it had run out of fuel after 9 years of service and the discovery of over 2,600 exoplanets. Kepler was deactivated on November 15, 2018, and will maintain its current safe orbit away from Earth. Thank you for joining us on this captivating journey through the legacy of the Kepler Telescope. We hope you've gained a deeper appreciation for the incredible discoveries and scientific advancements made possible by this groundbreaking observatory. If you enjoyed this video, don't forget to give it a thumbs up and share it with fellow space enthusiasts. And if you haven't already, be sure to subscribe to our channel and hit the notification bell so you never miss an update on our latest videos. As we continue to explore the cosmos and unravel the mysteries of our existence, let's remember the impact that missions like Kepler have on expanding our knowledge and fueling our curiosity. Thank you for watching, and until our paths cross again, remember, the sky is not the limit, it is only the beginning.